Welcome to the 2023 Earth Science Week webinar series based on our theme, Geoscience Innovating for Earth and People. Every year, the American Geosciences Institute creates a poster related to the Earth Science Week theme, which this year highlights many ways in which drones can be used to collect images and data that geoscientists can use to better understand the Earth. In addition to the poster, we worked with Matt Zimmerer from the New Mexico Bureau of Geology and Mineral Resources to create an introductory video about drones and how they can be used to study the Earth. Geoscientists make observations and collect data on Earth's features to understand how they form and change over time. In the past, these features have mostly been studied at ground level. However, having a view that is limited to the ground can make it difficult to study or map a large area. And what if a geoscientist wants to examine an erupting volcano or an iceberg floating in the middle of the ocean? There are Earth features that are inaccessible or dangerous to try to get near. Planes, other aircraft, and satellites have helped expand our view and can take pictures from the sky. Drones are often less expensive and more mobile than other technologies used for taking aerial images, making them one of the most common vehicles for taking videos and pictures of Earth's features. The technical term for a drone and its operator is unmanned aircraft system. The pictures from drones cover a smaller area, but are often much clearer than those taken by satellites or manned aircraft. Drones can also carry instruments to collect geoscience-related data, such as the magnetic sensor shown here. Other instruments include specialized imaging equipment that can help with mapping or other sensors to measure environmental conditions. There are two categories of drones that geoscientists frequently use for doing different jobs. Rotary wing drones have spinning blades like a helicopter that allow them to hover in the same place and launch vertically. Because they can hover, they are often used to take close-up images of features being studied. Rotary wing drones can also turn as they hover to view different angles and take panoramic shots of a large area. Fixed-wing drones are similar to airplanes and can take off from a runway or are launched using special equipment. Fixed-wing drones fly much faster than rotary wing drones and so can cover a larger area. They also maneuver much like a plane and can take smooth videos over a landscape. Both types of drones can take pictures and collect other data that is then processed using computer software. Images can be taken of the same area over time to map changes that occur, even if these changes are small. These detailed images can be used to make 3D computer models, allowing scientists to be able to study the area by interacting and experimenting with the model. Drones can also be used in mining to help find useful minerals and assess the safety of a mine. Drones can be used around volcanoes, earthquake zones, wildfires, and other natural hazards. Collecting data around hazards can help scientists better predict these events and assess damage from them. And drones can be used to monitor the effects of climate change. Taking pictures of glaciers, icebergs, forests, farms, and rivers can give insight on the health of these areas as the climate changes. Nowadays, drones are being used regularly to collect Earth science data, and new ways of using drones are continually being developed, so they are likely to be used well into the future. Are you interested in flying a drone? Classes are available to earn remote pilot certificates so you can help in the collection of data needed to understand Earth's features and processes. Next up, we will hear more from Matt Zimmerer about how the New Mexico Bureau of Geology and Mineral Resources and New Mexico Tech use drones to collect data to map and monitor changes in Earth's features such as sinkholes and to study surface processes such as erosion. In addition, Matt will describe how drones can be used in geoscience education.
Hi, everyone. My name is Matt Zimmer. I'm a geologist with the New Mexico Bureau of Geology and Mineral Resources, which is a research and service division of New Mexico Tech. The Bureau, as I'll call my organization, is essentially the State Geologic Survey. And during the last 5 or 6 years, I've had the great pleasure of working with my colleagues to explore the applications of drones for the State Geologic Survey. And I'd like to share a few projects that we worked on. I think early on, many people realized that drones are incredibly useful for understanding geologic hazards because you can study them in a safe environment. The area in southeastern New Mexico is somewhat prone to sinkhole formation. And in 2008, a relatively large sinkhole formed called the JWS sinkhole. And at the time, there were some attempts to measure the size of the sinkhole simply by taking an aerial photograph and comparing the size of the sinkhole to other features on the ground they could measure. And they at least thought that the sinkhole was on the order of about 111 meters across, but no real idea as to just how deep it was. So a few years ago, we went out and mapped out the topography of the sinkhole, shown here on the left. We show that the maximum dimension of the sinkhole is a little smaller, about 99 meters rather than 110. But we were able to show in pretty good detail the topography along the inside of the sinkhole and show that it's roughly about 31 meters deep. This is really important because if we ever want to go back out and measure it again to see if the sinkhole is getting bigger or maybe it's stable, we now have the data set to do that. Another place we've used drones is in northwestern New Mexico to study erosion. This is a part of the state that's really important. There's a fairly large gas reservoir in this part of the state, and there's some concern that erosion may impact the infrastructure related to this area. So we flew multiple drone surveys to map out how the drainages are potentially changing. So here's one drainage we mapped out the topography. You can see there's a fairly major road and some smaller roads, and if any one of these roads were to get destroyed, it'd be quite an expensive problem. So this is a very zoomed in, very small area comparing the stream about a year apart, August 2021 compared to July 2022. And what we found is that there are some parts of the stream that are eroding, shown in red, and other parts of the stream where sediment is deposited, shown in green. And if you map out the erosion and deposition over the larger drainage, you can start to understand just where the problematic areas are. Where is there erosion? Where is there sedimentation? You can also look at longer term records. So here's another stream in northwestern New Mexico. Shown in red is more or less where the stream was located in 1997. And with the drone, we can go out and map where the stream is located now. And we see that in some places, the stream has moved many tens of meters from where it was in 1997. So on the bottom right, you can see the stream's actually cutting into what looks to be like an old road. At the upper left, you can see the stream is inching closer and closer to some of the infrastructure related to the natural resources of the area. So this is a really good way to monitor how much erosion is happening and just how fast. A really fun project involved trying to understand the geology in northern New Mexico. This is home to the Taos Plateau volcanic field. Each one of these circular mountains is an extinct volcano. And cutting right through the middle of the volcanic field is the Taos Gorge, cut by the Rio Grande. It's a very impressive gorge. It's very sheer cliffs, but the steepness makes it hard to hike down, and you have a really hard time even when you're down along the cliffs making out big or large features. But the drone can help us by flying out away from the cliff. We can get these nice photographs, and we can begin to annotate them. So each one of these lines shows a boundary between different lava flows. And if you were standing on the rim looking down, you might say, well, here's one lava flow and here's another lava flow beneath it, two lava flows. But with the drone, we can actually see that there's the uppermost lava flow and then three lava flows beneath it. We can then combine that with other techniques like radiometric dating to put some ages on these lava flows. And so by combining the aerial cliff mapping with, say, geochronology, we can start building the story of volcanism in northern New Mexico. Lastly, drones are great for geoscience education. One of the things we try to do at the Bureau is make the science we do accessible to everyone, even if you're not a geoscientist. This is how I got involved in using drones, was for educational videos. This is actually an example out in California. Here you can see these fan-shaped features. These are alluvial fans, and then by flying over the fan with the drone, you can start to make out even smaller scale features like active drainage versus overbank flow. You can also create 3D models of geologic features with drones. This is an example of a feature called an angular unconformity, not too far from where the Bureau is located. This is where the sediments on the bottom part of the cliff are dipping in one direction, and the sediment layers on top are nice and horizontal. So this is a really fun way to allow students and teachers to explore features that they may not have in their own backyard, and spin them around and look at them in 3D. Lastly, we make a lot of guidebooks at the New Mexico Bureau of Geology. I don't think there's any better way to show geology than from the air. And this is an example of a guidebook we made about the Rio Chama in northern New Mexico. And here's the Rio Chama, and you can see the large canyon that it's cut, and the rocks exposed in the canyon walls. I think it's just a really fun and exciting way to make geology come to life. So that's a little bit about part of what I do for my job, and I appreciate your time. If you have any questions, here's my email address. Please feel free to reach out to me. Thanks.
Thank you, Matt, for sharing how drones can be used to study Earth's features. Next up, we will hear from Greg Foltz from the National Oceanic and Atmospheric Administration, who will discuss the application and innovation of sail drones in the study and prediction of hurricanes.
Hi, everyone. My name is Greg Foltz. I'm an oceanographer at the National Oceanic and Atmospheric Administration, or NOAA. I'm in Miami, Florida. I'll talk about an innovative technology called the sail drone. This is an uncrewed surface vehicle. You can see it here, this funny orange thing on the ocean. We use it to collect data to help us understand and predict hurricanes in the Atlantic Ocean. So they're powered by completely renewable energy. The wind acting on the rigid sail is what propels it forward. The solar panels absorb solar radiation that powers the sensors, the scientific instruments. You can see some of them there, especially on the top of the sail. That white dome on the back of the sail drone is how we communicate back and forth through satellite communication, sending the data back to us, for example. One of the innovative things about this is its design. So it was actually designed and has set a speed record, a wind-powered vehicle speed record on land. And a similar technology then was transferred to this ocean vehicle. Now we can use it to collect data conveniently in the ocean. This was a modified version. So we modified from the original version you see in the bottom right. It had a taller sail. It was more vulnerable to winds and waves. So this redesigned version had a smaller sail, lower center of mass, more rugged sensors, hopefully able to survive a hurricane. Something else that's innovative about the sail drone is that it can pretty much get to where it needs to go by itself. And that's through machine learning and artificial intelligence. This shows an example here. So we can just set locations in the middle of the ocean called waypoints. You can see some of them here. We're directing the sail drone to the south and then over to the east, and then back up north to get to that moored buoy there that you see, the yellow diamond and the circle. The shading there, the white and blue shading, and the white lines indicate the ocean currents. So the sail drone knows, based on the currents and the wind, it can adjust its sail automatically, adjust the rudder, and get to where it needs to go. That's very useful and very innovative. You can see we set a track there, the width of the track, so it knows to stay within that, not stray too far. Before this, we had to use things like moored buoys. These were stuck in one location, and they couldn't get into the path of a hurricane. We couldn't move them, so they didn't really do too well at getting us data in the strongest part of a hurricane. So that's an advantage of a sail drone. Also, the buoys require large ships to deploy them usually in a lot of sea days, so the sail drone is actually much easier and convenient to deploy. So we can deploy these with the small crane. We ship the sail drones, put them on the pier, use the crane to put them in the ocean. From there we use small boats. We tow them out usually a mile or two offshore to get them away from ship traffic. From there we use either a cell phone or a laptop through the satellite communications link, tell them where to go, and they're off on their mission. I'll show a short video here. This was a deployment that we did a couple years ago in Jacksonville, Florida. So it's a really nice way to do things, a nice convenient way to get data in the open ocean from these innovative sail drones. So you might wonder whether one of these sail drones can actually survive in a major hurricane. We had a similar question when we first started doing this a couple of years ago. We hadn't done this before. But we were willing to take a shot and see and learn from it and see what happens. So in 2021, this shows from September 2021. You'll see on the left, this will be a satellite image loop of a hurricane, and the position of the sail drone is the red line that's being traced out there on the map on the left. On the right, that's going to be the data that's coming in from that sail drone. We saw that coming in real time. It's going to trace out a bunch of different data that we got from it. So this is Hurricane Sam here, going back to the image on the left. Hurricane Sam, a Category 4, 145 mile an hour winds in the Western Atlantic. You can see the satellite image, the clouds coming up there from the bottom right. And it's tracing along that path. The orange dots show where the center of the storm is going. And the sail drone there, the red line. So we're directing it, trying to get it close to the center, get it through the strongest winds if possible, trying to hold it there. And you'll see, so the hurricane's going up. This is a video that the sail drone took inside the eye wall, the strongest part there of the storm. Waves of up to 90 feet, winds of up to 125 miles an hour. And it did really well. We were surprised, nothing broke really, and all the data came in and looked good. You can see it on the right here, these plots, the different colored lines show all the data coming in. And so we're excited. We're using this data to better understand hurricanes, and with the goal of ultimately improving hurricane intensity prediction. So thank you very much, and I'll be happy to take any questions.
Thank you, Greg, for showing us how innovations in sail drones are helping us better understand hurricanes. Next up is Richard Bishop, a professor from Virginia Tech, who describes how photogrammetry, LiDAR, and drones are being innovated to be used in underground mines. He also describes the many mining-related careers that use drones to collect, analyze, and apply data.
My name is Richard Bishop, so I am a mining engineer, originally from Petersburg, Virginia. Started my first mining job in 1999, so I guess 24 years ago. Kind of done a lot of different things in the industry, so everything from surface mining and aggregates to industrial minerals like titanium and phosphate, to underground construction here in Colorado, in metal mining and gold mining and tungsten mining. And then I actually also worked in the mining finance side of the business, so doing project evaluation all over the world, multiple commodities. And now I'm actually a professor at Virginia Tech. Around 15 years ago, I couldn't have imagined a drone or 3D scanning and some of the technologies that are available today. And so I used two different technologies there. One is called photogrammetry, which has been around for a very long time, and it's essentially taking photographs of a subject and making 3D models from those photographs. That's quite easy to do outdoors with GPS and sunshine and open spaces. Underground, it's a different story. So I have to adapt drones to be able to fly underground, to not crash, have light, and then have well-exposed photos to make those models. Now the other technology is called LiDAR. And so we're doing 3D scanning with LiDAR as well, which is adapted a bit better for the underground environment as it's providing its own light, if you will, in form of a laser. One of the primary applications that I do not only is the mapping, but the geotechnical work. So In the case of a new project that I've got now, flying drones underground, scanning underground mine pillars, and using that data in the office, so kind of taking that field data back to the computer in the office and determining how strong that pillar is. At what point might it fail or be overloaded, or looking at change detection. So if there might be an emergency situation, we may send a drone out ahead of us, kind of say, is the air okay? What does this look like? What are the structures that are in place? So we can use a drone to map that out ahead of us, but also tell us, what is there gas that we need to be aware of? Do we need to ventilate before we go underground? So the drones that we developed, you can basically instruct the drone where to go and explore. And so it can fly from outdoors to underground, autonomously explore the tunnels, if you will, underground, and then fly back out. And now you have that data set. You can see and visualize what's actually underground. You can measure the volume of the rock that's in place, or the volume of the excavations underground as well. You can take that data and say, well, is the rock competent? Is it safe for us to go underground? It's giving us new tools that we didn't have 20 years ago. A lot of these drones are getting miniaturized. So, the drones I'm currently building today, I've built some that are very tiny, but some of the sensors that we're using today are still larger, and they need a bigger drone to carry that payload, and even the cameras. But that technology is rapidly accelerating. So, where I just see things getting smaller, more affordable, maybe having the opportunity to work in unison as like a swarm. That takes someone that's capable of handling large sets of data, making decisions based upon lots of data. Information overload. And so, for me, it's quite exciting to kind of be on the forefront of that as well. And I think a lot of the students and engineers that I work with and teach are very well suited to kind of tackle those challenges. It's really pretty amazing, and it'll take, I think, most people's breath away to see the size of and the complexity of some of the systems that we work with. You don't have to necessarily be a mining engineer to be in the mining industry. So, you may really be into data analytics, and there's definitely a place for you in this industry. We need people with that skill set. Automation, drones. There's a lot of different things that can benefit the industry and the people working in the industry to make their lives easier, their job easier, to get more data. It's not what, you talk to a lot of people in the street and their first impression might be, oh, you carry canaries underground, or all mining is coal mining, or they just don't really have a reference for the industry, I think. And I think they need to dig a little bit deeper. It's a huge industry. It's international, it's global. It's probably in the county, or, not too far from the city you live in. You just may not notice that it's there. And you're gonna meet a lot of great people. You're gonna see science at work. You're gonna see people tackling challenges and opportunities, and kind of addressing the needs of society kind of from the ground level, right? Things that we need for supply chain start in mining. And I think it's a great opportunity for someone that particularly wants that hands-on work, or has some creative ideas, because there's a whole world of opportunity, I think, in the industry to start implementing new ideas and new technologies.
Thank you, Dr. Bishop, for showing us careers that are related to the use of drones in the geosciences. Next up is Dr. Norbert Jajan from the University of Miskolc, who will speak about the UNEXA project, which addresses the need for innovations in mining, such as underwater drones, that will advance our understanding of the sustainable and safe extraction of mineral resources.
Today's world is a challenging environment which requires a dynamic response and continuous adaptation to the successful and sustainable life for the society. This is also true for the raw materials needed for our life. Doesn't matter which way of the green transition we take, some primary raw materials input will be always needed. Our resources are getting depleted, thus innovation is one of the key elements in mining to provide the raw materials what the society needs in an environmentally sound and sustainable way. With one of the smallest economic footprint, the successful reopening of abandoned mines is a way to support our needs. UNEXMIN is a novel technology to send robots to flooded underground mines to collect geological and geotechnical information. The UNEXMIN project provided the working concept of the technology, and in 3 years between 2020 and 2022, UNEXUP EIT Raw Materials Upscaling Project further developed this technology, and the continuous development and innovation are the solutions to stay in the leading edge of our possibilities.
Over the last 3 years, the UNEXUP team has come a long way. During the journey, they were sailing on uncharted waters full of challenges and rewards. Many things were learned from the UNEXMIN project, and the experiences were integrated to the new project and most of all to the new robot. The UX-1 Neo and its controlling system were tested in various conditions. Probably the most interesting test happened in the Kőbánya mine, Budapest, where the first full autonomous dive was achieved. During this 3 years, 4 commercial missions were scheduled, but more sites were visited, all presenting specific difficulties. In the Hungarian Csor cast well, where a precise survey was needed for planning the renovation of the well, total disinfection was required, as it's a potable water source. In Solotvino in Ukraine, an abandoned salt mine had to be dived for risk assessment. The salinity is changing considerably with the depth. Therefore, a specific robotic cage was designed to carry the UX-1 Neo all the way down to 370 meters in a shaft scattered with rusty metal structures. Density change was not an issue in the South Crofty Mine, UK, but the visibility was almost zero, so the maneuvering had to rely almost entirely on the sonar data when diving to 300 meters in a narrow shaft to provide data for the engineers working on reopening this tin tungsten mine. The UX-1 Neo's capabilities were not only harvested in the industry, but scientific research was also conducted. In the Ekton mine heritage site, old mine workings were rediscovered and mapped so we can have a better understanding how mining was done in the 18th century. 2 cave research missions were also carried out. In the Molnár János cave, Hungary, the maze-like passage structure with its twists and turns was a perfect test for both navigation and mapping, while resulting in a detailed geological map of cave sections. The Hronica Abyss in the Czech Republic is known to be the world's deepest underwater cave. On a previous expedition, an ROV reached 440 meters here. In August 2022, the UX-1 Neo broke the world record during the mapping of the cave to a depth of 450 meters. From the gathered data, it's obvious that the cave goes even deeper. Good perspective for the UX-2 Deep, as it is depth graded to 1,500 meters, perfectly capable of continuing the exploration. Although the project ends, development is ongoing with our commercialization partner UNEXMIN Georobotics Limited, who offers the robotic survey on the market and seeks for new challenges and opportunities.
Thank you, Dr. Jajan, for showing us how UNEXUP uses underwater drones to explore abandoned mines. Lastly, we have Hannah Ziegler from Vanderbilt University, who will talk about lessons she developed that introduce middle and high school students to building, coding, and collecting data using drones.
Everyone, my name is Hannah Ziegler, and today I'll be presenting an example of a drone-based instructional project that I developed for applications in secondary STEM classrooms. This presentation is based on my recent work as a high school math and science teacher, but now I'm currently a doctoral student at Vanderbilt University. First, I'd like to introduce you to the Idaho Drone League, or iDrone program. The program offers workshops for secondary students, and the curriculum includes building, coding, flying, mission planning, as well as a poster session. Most recently, the program has developed a module on robotics as well. If you're interested in learning more, I encourage you to visit their website at idroneprogram.org. I adopted the iDrone curriculum to develop this 3-week-long instructional project to teach climate change to 9th grade Earth and Space Science students. You can access the lesson plan online by scanning the QR code or typing in the link right below it. In this project, students are given the task of designing a drone attachment to solve a problem of their choice related to global warming and climate change. This not only requires students to understand the implications of climate change on human society, but also to engage in the engineering design process. Here's an overview of the project broken down into 3 major parts. Please note that this estimate is based on 50-minute class periods, so your timeline may look a little different from mine. The first part of the project consists of drone building. The iDrone kits provided all necessary parts and tools to assemble a small classroom drone. Many students often find this building process enjoyable because it is highly hands-on. Throughout the lesson plan, I embedded links to self-paced video tutorials created by the iDrone program. Students could rewind or use closed captions to assist with individual learning needs. Following the assembly, students tested the pre-programmed drones using a mobile app called CupDrone. They were able to fly their drones safely with the provided pedestals and holding brackets that prevented them from flying freely within the classroom space. During the second part of the project, I introduced students to drone coding. I provided written instructions along with the sample codes and video tutorials, which were sufficient for introducing students with little to no prior experience with programming. The original iDrone curriculum utilizes 2 different platforms for coding, Arduino IDE and MIT Scratch. Here I show some sample codes from each program. The most basic code starts with running the front left motor for a second, stop continuously in a loop. You could also add in optional coding challenges to differentiate for advanced students, like the example I included in my own lesson plan. The final part of the Drone Climate project engages students with engineering design. The instructional time could vary based on how you choose to modify for your own classroom. First, student groups researched and identified a list of potential problems caused by climate change. They collectively decided on a single problem and solution that they initially sketched on paper. Then students used Tinkercad software to 3D design their prototype, which was further developed using 3D printers. During the final phase, students collected feedback from peers, teachers, and anyone in the school community to inform areas for improvement in their designs. Here are examples of student worksheets that illustrate their brainstorming of problems, solutions, and visual designs. These are some of the designs that they created using Tinkercad. Nearly all of my students were completely new to computer-aided design or 3D printing, but they caught on very quickly using the basic tutorials available on the Tinkercad website. And lastly, here are some samples of students' final products after they had been 3D printed. And that's it. Please feel free to contact me if you're interested in piloting this lesson or some modified version of it. I'd also love to hear about any feedback you might have for me. Thank you for watching.
Thank you so much, Hannah, for your work in developing these lessons and for sharing them with us today. We appreciate the time all our speakers took to share their expertise on the use of drones in the geosciences and in earth science classrooms. Thank you so much for your attention to today's webinar and the presentations on the use of drones in the geosciences. I'm Lindsay Mosa, and I'm here with my colleague Lauren Braze to continue the conversation with today's speakers. Please continue to let us know if you have any questions by putting them in the chat. But to get us started, I'd like to hear from a couple of our speakers on whether you expected to use as much technology as you do in your jobs. And did you learn these skills in classes, or have you learned them through on-the-job training?
Hi, I'm Matt. I guess I'll jump in. So the answer to your first question, did I ever envision using drones in my job? That would be no, never. As I was an undergrad, did I think that would be an opportunity for me, which is really a testament to sort of the technological innovations that that these drones present, there's a bit of a learning curve to using them and flying them and doing it in a safe way and according to regulations. But they're very stable instruments, particularly the quadcopters. They're very forgiving. And so yeah, it's been wonderful as an avenue to advance my career. I think the second question was, how did I get into this? A little bit on my own, and a little bit of interacting with some other folks. There were some students I was going to school with who sort of exposed me to drones and got me interested. But I took some classes to really make sure that I was using them in a safe way according to the FAA. So a little bit of both, learning from friends and other drone enthusiasts, and then kind of online learning and some workshops with professionals.
I could jump in as well. So this is Richard Bishop. So, when I graduated originally more than 20 years ago, I certainly didn't even know drones would ever exist. It was purely science fiction at that point in my career and life. I at least had the opportunity to fly in some helicopters and airplanes and do aerial surveys as part of mining operations. But, I think for me, when I made the decision to do a PhD, I thought back about some of my time in industry, both on the contract side, where I was, restarting old mines, some of which were more than 100 years old, or doing a lot of international travel and visiting some operations that may not have been up to the same standards that we appreciate in a modern mine today. And seeing how quickly drone technology was advancing at that moment, and trying to be on the forefront of pushing that for the applications that would benefit me in my past life in the mining industry.
I'm going to give us a pause to see if any of our other presenters want to jump in. Thanks, Hannah.
Yeah, I can add, coming from an educator's perspective, I had no idea that I was going to be working with any kind of drones. I had some interest in some sort of emerging technologies to use with students. I simply got lucky because I got in touch with a faculty member at the University of Idaho who was working with drones, more for water resources and agriculture, but then he expanded his work into secondary science and STEM education in the state of Idaho. And at the time, as a classroom teacher, I got in touch with him, and it was a huge learning curve for me as well to just to learn enough technology to facilitate the instructional activities for my students. But it was definitely worth all of it. And so for me, it was really important getting in touch with some sort of drone expert, and that partnership was really helpful for me getting here.
Norbert or Greg?
Yes. When I finished my university, roughly 20 years, a bit more, then we really rarely heard about drones. I would say I can remember in some geophysical applications which was mentioned, but we never had the experience to see it on the field. But I started in the laboratories. I use a lot of big instruments from electron microscopes and different, and I see two big changes on the field. One was with the handheld instruments, when the different technologies could go to the field, and the other big revolution was the drones. And with miniaturization, when you combine the different measurements and drones, you have more and more possibilities, and it's extremely changing. Definitely, it's like a logarithmic curve where you can use these tools in your field. Yeah, definitely, it's changed a lot.
Yeah, so in my case, definitely drones did not exist when I was in school, in college and grad school. And so there's mostly moored buoys in terms of oceanography. If you wanted to measure the ocean and the atmosphere at the same time, you're pretty much limited to moored buoys, which were stuck in one place. So sail drones came along about 10 years ago. And that was pretty exciting because now that's basically a moored buoy that you could move around. So that was nice. And then the ability to put one, the engineering to be able to design one of these that could be put into a hurricane was only about 3 years ago. So it's been a really recent and a pretty rapid development because we've partnered with a private company, the government and a private company, Saildrone. So that's worked really well. And it's enabled a lot of outside investment and a lot of scaling up pretty quickly and the ability to do this. So that's been pretty exciting. And we've had some success so far. We're still doing it. We have 10 Saildrones out there this hurricane season. So yeah, I never would have thought that, when I was in grad school, that this would be what I'd end up doing. So yeah, it's been a fun ride so far.
Awesome. And all of your answers kind of addressed our theme this year, which is geoscience innovating for Earth and people. And so just the fact of the advancements of technology, the fact that new things are coming along, and the different partnerships that it takes to make geoscience progress like this. So thanks for all of your answers. We're going to jump to our first question in the chat. And Matt, I think it's for you. It's, does the use of drones in geological studies operate with the same techniques as remote sensing?
Yeah, I think to a certain degree. I think some of the other remote sensing techniques, getting high resolution topographic imagery is certainly something that's been done with say LiDAR out of fixed wing aircraft. I think one of the things that is great with drones is it's sort of on demand data. So, for example, say there's a new geologic feature, a debris flow that happens, as opposed to a very expensive and perhaps time-consuming campaign to get out and get remote sensing data. The ability to essentially get out as quick as possible to a new geologic feature and to be able to measure it is one of the great things for us. Particularly, we're at a state survey, some of our projects, we want to know how geologic features are changing on a very rapid timescale, say over the course of one summer, and so we can go out and make these flights really as much as we want. So I see a tremendous amount of overlap with some of the traditional remote sensing techniques, but the ability to kind of get it when you want it for fairly cheap and at sometimes a higher resolution is one of the more attractive aspects of drone technology for me anyways.
Awesome. I'll give anyone else a chance to jump in if they'd like to respond as well.
Yes, because I think I'm in a really unique situation. We could design our own drone to get in an environment which wasn't accessible earlier. So we had the possibility to dream something and send robots somewhere where couldn't go earlier by humans or other technologies. So in this case, yes, we use a lot of similar sensors than remote sensing, as Matt mentioned. Of course, many times it should be fine-tuned for our applications. For us, especially, the miniaturization was really a big question. So can you put it in the drone? Can you fly it enough time? Do you have the energy for it? And the other thing is the underwater. For us, this is really a big difference. What to sense. I mentioned that I could measure much easier and design a drone to the moon, because in vacuum you can sense something from tens of meters, but 10 centimeter of water usually shields your visibility or shields your different sensors. So we really had a hard time to find our sensors in that case. So I would say it's a mixture for us.
Sounds like a tough challenge to overcome. All right, our next question in the chat is for Greg. In terms of the sail drones, what are the dimensions such as height, width, and rudder depth?
Yeah, so well, they're about 10 feet tall, so that the rigid sail goes up about 10 feet on the Hurricane drones. and they're about 15 feet, no, sorry, 23 feet long, and about 3 feet wide. And the rudder goes down about 6 feet below the surface of the ocean. So it's kind of deceiving if you just look at them from the surface. They don't look too stable. They look like they might fall over, but they actually have a pretty solid, heavy rudder. They're about 1,000 pounds total. So they're really stable, and they take a beating during hurricanes. We've measured waves of up to 93 feet, and they've been in winds up to 140 miles per hour, and they've actually flipped over completely. They'll go down waves, giant waves sideways, and then flip when they get to the bottom, and they'll roll 180 degrees, so completely upside down, and then they'll pop right back up and keep going. So yeah, it's a good, really nice engineering on them. They work pretty well in hurricanes.
Yeah, I'm imagining that took quite the iterative design to make sure that functioned in a hurricane. So
yeah, and
definitely.
we're still redesign, still experimenting and finding things they break, and we try to make them stronger. So yeah, definitely still developing and improving.
Awesome. Well, our next question in the chat was for Richard, but I believe you answered it already about keeping the drones airborne. So I'll let you elaborate on that if you want. And I'll also include the next question for you that was in the chat, which is, how is LiDAR used to perform geotechnical analyses, and can drones take rock samples from mines?
Sure, sure. So, yeah, to address the first question, which I did put some commentary in the chat. So, I'm doing a lot of different things with drones right now, testing, whether it's photogrammetry or LiDAR that I'd mentioned in the video. The LiDAR, when it's a 360 LiDAR, can actually perform that localization. It can perform that position hold. It can help prevent collisions all on its own, even in the absence of light and GPS. Other drones that I've built, when it's coming to just using a typical camera sensor, even on a commercial drone like from DJI, they have optical flow sensors already built in. The big issue there is there's no light underground. So then we have to start addressing the lighting situation. So the downfall to using an off-the-shelf drone is they're not quite as easily it's not quite as easy to modify them. So it's quite a bit easier if you can build your own systems. There's a lot of open source software out there to do that. And you can start integrating various sensors to start testing underground. So again, like with photogrammetry, if I'm just using a camera sensor to collect pictures of a pillar, or for one test case that we're testing now, we're using a drone to take images of the roof underground in the mine to try to determine if there is a potential for rockfall. We do use some systems for stabilization, so you can use a simple and inexpensive two-dimensional LiDAR system, or laser rangefinders, or even optical flow, kind of like a computer mouse that's detecting if there's any movement of the drone. Otherwise, outdoors, you're able to use your GPS or GNSS signal for localization. So we just can't do that underground. And then I think I know the person that asked the other question. So with the geotechnical characterization, so we're not actually at the moment, using drones to collect rock samples. I suppose something could be designed in the future to do that, but primarily we're using the 3D models, whether they're generated from LiDAR or photogrammetry. We're getting and pushing the density of those point clouds. So the 3D model data that we're collecting, we're making sure that it's of sufficient quality that when we generate our 3D models, we can actually map joint sets and discontinuities as inputs to our numerical models. We're looking at like the strength of a pillar that you had seen in that video. Good questions.
That's great. But yeah, it makes it sound really versatile for, what you're using it for. So that this is fascinating. I love hearing all these functions of drones. So the next question for any of our presenters, really, is it possible to use drones to get better resolutions for aerial views that can be that is better than satellite images that come from some distance away? So I think in terms of remote sensing data analysis.
Yes, definitely. So this is the big advantage. You can go really close. So actually with drones, you can fly over the ground in 3 meters. So you can really have resolution, even sub-millimeter resolution in your images. So, and actually you can much slower scan your area than, for example, in any manned aircraft. So this is where the drones are the big advantage. And just to add, we halfly made a tool which is possible to sample with our underwater drone. We were planning to do a kind of cheap samples, use a driller to do cheap samples, and with a water pump suck those tiny particles. We built a robotic arm, but unfortunately the COVID time stopped the development. So this was, we had to stop with it. So this was the only one thing which we couldn't turn in our project to reality. So thanks.
Great. Yep. Hannah, the next question is for you. The person asks, how did you get started with the iDrone program, and what resources do you recommend looking into for schools that want to join a program like this?
Yeah, that's a great question. For me, connecting with the iDrone program, it was just word of mouth at first. But in Idaho, at least, there's a STEM Action Center that has a lot of initiatives and programs for STEM teachers. And I actually participated in that summer externship program as well. So it was a great opportunity for them to connect local teachers with industry experts, faculty members, et cetera. And you spend the summer developing lesson plans and having some expertise and support. So that was a great way to get involved for myself. And I know other teachers who use that opportunity. And then they would implement those lessons during the school year. So you might have to do a little search for similar opportunities wherever you're located. The other thing I needed to seek out was funds and applying for little grants because drones cost money as well. So I had to take initiative to do that. And I had to look for collaborators, but also it's important to have some support from admin or just institutional support. So if you have that available, getting with your colleagues, I think it makes the experience a little easier with the whole learning curve. And another avenue you could look into is conferences, getting in touch with other educators who are interested in working with drones in education. And I presented this work, for example, at the National Science Teachers Association. We probably look into engineering education conferences too. I think that'd be a great way to connect.
Great, thank you. We're always looking for things to help out educators get geoscience concepts and technologies and innovations into the classroom. So it's really helpful to get that information. Our next question in the chat was from a researcher who wants to use drones for more than just capturing images, since most of us think of it as, that's what drones are good at doing. So what factors kind of affect the flight duration of drones and the resolution of the images they capture? And also, does anyone know if it's possible to program a drone to fly for 24 hours?
I'll jump in there. So, I mean, another project that I've worked on in the past is building drones with methane sensors. So, for example, like a laser methane sensor that can do laser or methane absorption. And so that's, another application where I was, taking images to build 3D models, but also using a very different sensor to try to find leaks and try to improve environmental quality. So there's a lot of different things you could get into, I think, besides just aerial images. The photogrammetry that I mentioned, using your two-dimensional photos to create 3D images, is pretty straightforward today. And as far as, flying for 24 hours, it's pretty difficult with an off-the-shelf drone, but there are hybrid systems that I've seen available out there. There's tethered drones where you could have a cable running down to the ground to provide continuous power. So there are some options, but I don't know that anyone's produced anything turnkey that would fly for much more than an hour, hour and a half.
Yeah, and I can jump in a little bit there. I think part of the question was what factors impact the the length of a flight. So I think the biggest thing is the weight of the drone and the battery system. So the more sensors you have on there, that might impact it. It can get pretty windy in this part of the world in the spring, and so if you're always flying into the wind, it just takes more power on your aircraft. So one thing we try to do is keep good tabs on the weather, so we're not going out and fighting the wind, and which I think is a really fun part of flying the drones. I mean, the science is great, and we all love that, and flying them is just really fun too. And I think part of that experience is keeping tabs on the weather and looking for these opportunities where the lighting's going to be right, and the wind's going to be just right, and sort of having it all come together. So yeah.
Great, thank you so much. This has been a very informative talk today, but unfortunately we are out of time for questions. If there are any questions that were not addressed by today's audience, please feel free to email us at webinars@americangeosciences.org, and we'll make sure to get those questions to the appropriate speaker, or maybe all the speakers, because it sounds like there's a lot of crossover between the work that you all do. We'll be posting the recording of today's webinar on our webinar webpage and our YouTube channel within a week, and we'll notify you once the recording is available. Lastly, you wanted to share the upcoming webinars in this series. Next up, we have a webinar on photogrammetry and its applications, including in earth science classrooms. We hope to see you there, and thank you so much for attending today's talk, and thank you again to all of our speakers.
Thank you. Goodbye.
Bye, everyone.
Thank you. Bye-bye.